So to round the topic off, I would really like to take a little bit of time and say, how can we make A-CDM sort of A-CDM 2.0? So how can we make it even better than it is today? And before we look forward, quickly want to take a small step back. Because what's really interesting is aviation comes from an age where you had a control tower and it was a little terminal, and there were 2, 3, 4, 5 aircraft a day, and there was nothing but a schedule. And an aircraft would come or it wouldn't come, or it might come too late. Airports would call each other, hey, this flight is actually delayed today. So very primitive, and it worked because there was not so many flights. But as flying has gotten cheaper and more accessible, and in many big countries like China and India, the middle class has developed, the demand for air travel has boomed, and airports have gotten bigger and bigger and bigger. The demand for air travel has increased even faster, and one of the problems is that the demand for this air travel has increased faster than airport capacity, because airport capacity is very expensive, takes a long time to build and to develop. So there's this pressure on the system in order to make sure that everything still goes through. And let's not forget, the way that we communicate with aircraft, VHF radio is a World War I technology. The way we locate aircraft, even still today, radar is a Second World War technology. So the world has changed, but the way we manage aviation operations has not changed that much, and that's one of the problems. And if we then look forward, these are numbers from IATA, pre-COVID, obviously, and they predicted that between 2017 until 2037, the demand for air travel would even double, and that's a medium scenario, right? So that's not overly optimistic. You can see the green line here, which is the optimistic scenario, is even more. And sure, COVID will play a role and will hit these numbers, but also if we look back, then we can see other crises, such as 9/11 and 2008 financial crisis. They did impact aviation, but if you zoom out then again and look at several decades, it's just a small hiccup in the line. And maybe COVID will be a bigger hiccup, yes, and maybe it won't double from 2017, but it's pretty sure that we're still heading in that direction anyway. So the whole reason why A-CDM was introduced, in order to make everyone collaborate much more closely, in order to make better use of the available resources, is already required today, but will be even more required going into the future. So from my perspective, A-CDM is really an optimization framework. We're trying to make the best use of the available infrastructure and resources. And when we look to an airport, that means the best use of aircraft stands, taxiways, runways. But if you look at the airspace, airspace is limited anyway you look at it. So we need to make better use of it in order to accommodate that growth. So then if we look at it from an optimization perspective, to get a better, more optimal outcome, a better use of that scarce resource, there's basically two main components, the input data and the optimization model. And I think what A-CDM did is that they introduced a collaborative framework where people share data with each other, where they talk about in common words. So they use the same definition. So when an aircraft takes off, everyone understands exactly what that means. And it doesn't mean that one person thinks it left the gate and the other one thinks it actually left the runway, because that was actually the case. So introducing common definitions, sharing data, that has already made a big step in the optimization part, in the model. Is there room for improvement there? Yes, sure. Even there, machine learning and AI, which is typically very well suited in order to make these optimization problems based on a lot of different input variables, can bring improvements there. But today I want to focus on what goes into the optimization. There's a term, GIGO, which is garbage in, garbage out, that typically applies to these optimization problems. If the input data that you put into the optimization model is not accurate, is not good, then it doesn't matter how great the model is, the output will still be suboptimal. And I think that's one of the problems that we face today with A-CDM. And so I want to highlight two key things that I think we can improve today. One of the most important milestones in A-CDM has to do with when the aircraft goes off block. And why is this one important? Because it basically determines when is the aircraft introduced into the system, and everything else from there, the taxiway usage, the runway usage, the airspace usage, all depends on that moment, right? And not for one aircraft, but for all the aircrafts together. And currently, today, the ground handler is responsible for continuously updating the target off-block time, which is the time when he thinks he'll be ready for the aircraft. Now, what we see, the data that you see on the slide here, is some research that we did on data that was available from some of our customers, is that the accuracy of the target off-block time is actually quite low. And besides that, it's not only how accurate is the information, but when do you receive the information? So what we typically see is that the ground handler waits until very shortly before the scheduled departure time, and only then updates the target off-block time. And even though it might be accurate then, the information comes so last minute that all the proactive power for all the other stakeholders has been lost. Now what we do is we create a predicted off-block time. And the predicted off-block time is basically an automated variant of this target off-block time. So we can use generic AODP data, so the data that every airport has, and then we can already easily outperform the TOBT. Now, obviously, if you add real-time data from the turnaround, so what's happening inside the turnaround, then the performance will become even better, especially as you move closer to the actual departure time. Maybe just a small example to highlight why this is so important, because it's one of these things where it just looks detrimental until you realize that the full scope of it. Let's say a ground handler is handling an aircraft, which is going to be delayed. But at the moment when he sees several things happening and thinks it might be delayed, he thinks, I'm not updating the TOBT just yet. Maybe just because he's busy, he forgot. Or maybe because he actually thinks they might be able to make up for the lost time, right? So he just decides to not update the TOBT, something that happens very often. In the meantime, in the airline hub control center, there's people that look into incoming flights, outgoing flights, transfer passengers on all of these flights. And they still think that the aircraft's going to leave on time. So another aircraft that comes in slightly delayed, they book the passengers to another flight. So they put them in a hotel, they're booked onto the flight for tomorrow because they will never make the minimum connecting time to this aircraft that's going to be delayed. In the meantime, the gate planner from the airport, he checks the gate plan and he actually thinks, yes, everything is still on track. So no need for my attention. I don't need to make any changes. Then, of course, the flight delays. So what happens? These passengers from the incoming flight could have made the flight. The flight that is going to the same stand next is actually already waiting, while the other flight is still there because the update came too late and the gate planner didn't realize. So now one delay is causing another delay. The aircraft that's waiting is burning kerosene, so cost for the airline as well. And in the meantime, in the airspace, we got the scarce resource of airspace. We have a slot that's just empty that could have been used otherwise. And further on, we'll have a problem because the slot wasn't planned for, and all of a sudden there's an extra aircraft that we need to accommodate. So you can see how it all trickles down into the entire system. So if we have earlier and more accurate information about when the aircraft leaves, all of that stuff downstream can be better optimized. Now, the second thing that I shortly want to talk about is feedback. And I want to use the example of driving blind. If you're in Amsterdam, for example, and you need to go to Berlin, and someone will tell you, close your eyes and you'll drive straight for like 20 seconds, then you turn left 90 degrees and you drive another 10 seconds, and he will explain you the entire way to Berlin. Would you feel confident driving to Berlin like that? I don't think so. The morale in this story is that you need feedback. So you need feedback on what you're doing so that you can actually steer, so that you can see what's happening and act and react in order to make sure that you achieve your goal going to Berlin. And the same goes for managing turnarounds. Because the second point I want to make is that the CDM milestones are great, but between in-blocks and off-block, that's a huge black box, and that's not being addressed today in A-CDM. And therefore, airlines and ground handlers, how can you manage what you can't measure, right? So whatever happens in that turnaround, they don't get the feedback on it, and they cannot act and react on it. So, for example, if a fueler comes late, typically you will see someone stand should the tutor not have been here, or the pilot? Why is the tutor not here? Should have been here like 10 minutes ago. That's 10 minutes lost. That's serious time. If you have real-time information about all the important milestones of the turnaround, you can directly see when things go wrong, and you can directly act in order to mitigate the impact of that on your overall on-time performance. And it's not just about reducing delays, because even if you have 0 delays, if you have all that time about all that data, and that's actually what Chris de Bolle also said, if you have all that data, you collect all that data about your operations, you can analyze it and you can find room for improvement. So an airline might actually be able to do quicker turnarounds, and overall that have, that one turnaround that's shorter, whatever. But if you have a 2-minute save on all your turnarounds, then look at your flight schedule again. Can you fly an extra leg somewhere in your entire schedule? Reduce the cost of a turnaround, either because you get a better grip on your suppliers that you're paying to deliver a certain service. Are they delivering? Do you actually know? On the other hand, a lot of airlines and even ground handlers, they got quite a lot of staff to sort of break the black box problem for them, right? So they have a lot of staff at the aircraft to visually observe what's actually happening, what happens. But human is not perfect. If he's standing on one side of the aircraft, he cannot see what's happening on the other side. So you can, by getting this full real-time visibility, you can also reduce your cost in that aspect. And last but definitely not least, this pressure on the aviation system that I talked about also has negative effects on safety. The pressure is on, people need to deliver, operate in high speed, full pressure, limited space. So adhering to standard operating procedures and following safety guidelines is crucial. Unfortunately, it doesn't always happen. By monitoring what's happening in the turnaround, you could potentially also monitor safe behavior, and therefore make aviation safer as well as more optimal. So thanks. That was my contribution.